Alright, so for this next project, we're going to simulate the transient response of an electric circuit that involves a resistor, an inductor, and a capacitor. So what we're going to do is we're going to add a voltage source, and then we're going to add a switch that's going to close at a certain time during the simulation, and then we're going to see what the transient response of the circuit is. So basically what I want to do is simulate the following circuit. So we're going to have a voltage source that's going to be a DC voltage source of 10 volts. And again, this is 10 volts direct current. And this circuit is going to have basically a resistor, an inductor, and a capacitor all connected in series. Now we want to switch the voltage source during the simulation. So we're not going to start with the voltage source connected to the circuit. So in other words, we're going to have essentially a switch over here that is going to be closed at a certain time during the simulation. So we're going to use some generic blocks from Simulink and a switch for this circuit. So we're going to simulate a circuit that has a resistance of 1 ohm, an inductance of 1 millihenry for the inductor, and a capacitance of 1 millifarad for the capacitor. Now, before we actually simulate the circuit, usually first what you want to do is derive some mathematical equations for what you're trying to simulate so that you can see if the model behaves the way you were expecting it to. This is very typical for any simulation. First you do a design, then you do a model, and you simulate that model, and you kind of try to see if that matches your hand calculations or what you were expecting from the theory of how you think the model is going to behave. So real quick, let's go ahead and derive some equations for this circuit. And this is a little bit related to electrical engineering, but basically the voltages across each one of these components is going to have a certain equation for it. So we're going to call the voltage across this resistor VR, the voltage across the inductor V sub L, and the voltage across the capacitor V sub C. Now the voltage for a resistor is given by the following equation. So VR is equal to the resistance times the current that flows through that resistor, I of t. So the current I as a function of time t. The voltage across the inductor is given by the following equation. So L, which is the inductance of the inductor, times the rate of change of the current, so di dt. And then lastly, the voltage across the capacitor is given by the following equation. So the initial voltage across the capacitor, so it matters whether or not the capacitor was charged previous to us closing that switch. So VC0, so the initial voltage across the capacitor, plus 1 divided by the capacitance times the integral from 0 to t of the current, so I of tau d tau. Now again, I know that this is a little bit related to electrical engineering, but basically the equation that gives us the voltage across this entire circuit, Vt, so the voltage as a function of time, is going to be the addition of all the three components. So the addition of the voltage across the resistor, the inductor, and the capacitor, for which we have these three equations over here. So essentially what I'm saying is that the voltage across the entire circuit, and let me actually change colors, so V of t, which again is the voltage across the entire circuit, is going to be equal to VR plus VL plus VC. So now we plug in these equations over here, we will get that the voltage V of t is going to be equal to R times I of t plus L di of t dt plus Vc0 plus 1 over c times the integral from 0 to t of I of tau d tau. So now what we can do is we can say, well, we're going to take the derivative of both sides of this equation, and we can also assume that the initial voltage across the capacitor, so this value over here, Vc of 0, is going to be 0. So essentially we're saying the capacitor was discharged prior to us closing this switch over here. So if that's the case, then again, if the voltage source, this one over here, is a constant voltage because it is a direct current voltage, then the derivative of that is going to be simply 0. So we can say then that this equation is going to become 0 because again, the derivative of v of t is just 0 because v of t is a constant, and then times r times the derivative of I. So again, we're taking the derivative of all the terms in this equation over here. And I'm actually going to divide every term by the inductance L. So I'm going to say R over L times di dt. That would be this term over here again. Taking the derivative of that term and then also dividing it by L. And then we're going to do the same thing for this term over here. So the L is going to be divided by L, so that goes away. And then we're taking the derivative of that term, but that's already a derivative. So now it's going to be the second order derivative of di of t. So di squared dt squared. And then we're saying again that the initial voltage across the capacitor is 0 volts. So that term goes to 0, and then we get 1 over L times C, so this term divided by L, times the derivative of this term over here, but the derivative of an integral is just going to be that term. So this is going to become I of t. So now here, and let me actually switch colors. Now we have an expression that's going to give us the voltage, or rather the current, through this resistor. So the current that flows this way, I of t, and then the voltage across the entire circuit here is going to be 0 before we close the switch, and then it's going to be simply just the same voltage once we close the switch and we complete the circuit. So this, as you can see, is a second order differential equation, and we're actually going to simulate that, and then the response in Simulink should match the second order differential equation. And what we're going to see is that it's going to look something like this. Now this is going to depend on the values of the inductor and the capacitor and the resistor in the circuit, but in general, and let me switch colors again, if this is time of S, and this is the current, I of t, and this essentially, let me change this is going to be current in terms of amps, and this is time, of course, in seconds. So essentially the current is going to be 0 before we close the switch, and then once we close the switch, so we can say then that at this point we're closing the switch, then the response should be something like this. So it's going to be a damped oscillation that eventually settles down at 0. And again, we can see that from this differential equation, and this occurs once we close the switch. So before we close the switch, of course, there's not going to be any current because the circuit isn't complete, and the voltage across the other side of the circuit, so V of t, is going to be also 0. But once we close the switch, current starts to flow, and the transient response should look something like this. So now let's go into Simulink and let's see if the simulation matches our calculation. Alright, so I have a blank model here and I've called it the electric circuit model, and of course this is going to be available for download with the lecture resources. But essentially what we want to do is we want to have a DC voltage source and a resistor, a capacitor, and an inductor connected in series. We want to have a switch that closes at a certain time during the simulation, and then we want to see what the transient response of the circuit is going to be. So of course, to get all the components, we need to go to the library browser, and in here you can go to the Simscape menu. Again, in the Simscape menu is where you can find the electrical, gas, hydraulic, magnetic, mechanical components, everything that's physical networks. So let's go to electrical and to electrical sources, and I want again a DC voltage source. So this one over here on the right. Let me add that to the model. And we also need a capacitor, a resistor, this one over here, and an inductor, this one over here. And we also want a switch, which is found over here. Now we want a couple more things. Again, we want to measure the current that flows through the circuit and the voltage across the circuit. So we're going to need some electrical sensors. Again, a current sensor and a voltage sensor. And again, remember that for any physical network, you need to have what's called a solver configuration block in your model. So this block over here. So let's add that into our model. And we're also going to need the physical signal to Simulink signal converter and the other way around as well. So let's go ahead and search for a converter here on the search bar, or actually it's right here in the same window. So this converter and this converter. And one last thing that I want to add is a clock, which again gives us the simulation time. And I'm going to explain here in a second why I want to add that to the model. But now let's go back into the model and let's go ahead and build our electric circuit. So let me move stuff around. All of the components, of course, are dropped here in the center. So here's the voltage sensor, current sensor, the switch, inductor, resistor, and the capacitor. And here's our voltage source. So let me put the voltage source here to the left, and let me rotate all of these elements. So again, if you're on a Windows computer, you can simply click Control R for rotate, and that rotates the elements. So I want all of them aligned vertical. So I want the resistor over here, then the inductor, and then the capacitor. So you can see here that Simulink already automatically connected all of these. And I'm going to put my voltage source over here. Now again, I want this switch because I want to be able to switch in the circuit during the simulations. If I connect this switch here, what that's going to do is until I give it a signal here to this physical signal port, the switch is going to be an open circuit. So there's not going to be a closed circuit over here until this switch closes, and we can tell it when to close with this signal over here. So it's going to be useful again because we want to see the transient response of this circuit. Now again, I want to measure the current that flows through this circuit. So let me move this switch to the left. And for current measurements, we basically need to connect that in series. So the current sensor is going to go over here, and the voltage sensor is going to go over here in parallel with all of the components. And I forgot two blocks to add, so let's go back to the library browser. I'm going to need a scope, of course, to be able to see our results. So let me go ahead and search for that. This one over here. Let's add that to the model. And I'm going to need a go to and a from block as well. So these two over here, from and go to. I believe that's everything I need. Let's go back into our model now. And again, they're dropped over here. So again, I'm going to use this from and go to blocks just to keep things a little bit more organized. And I need a physical signal to Simulink converter to be able to connect to this go to block. So let me get rid of this wire over here. Just this one over here, just the wire. Let me move this around. I want to get rid of this wire. Okay. So now, again, I need a physical signal to Simulink converter, which is this converter over here, so that I can connect the output of the sensors to the go-to block. Again, remember that Simulink blocks, which are the ones in black, only take a Simulink signal, but these sensors are physical signals. So I'm going to do the same thing for the current as well. So let me add a go-to block over here, as well as a Simulink, or rather physical signal to Simulink converter. This is going to go over here, and this goes over here. So I'm going to rename this simply I for current. I'm going to rename this go-to block V for voltage. And now I'm going to take this from block and make a copy of that. And I'm going to have my, let's put the voltage on the top. So again, you got to hit update tags so that Simulink knows where to find the tags. So this is going to be my voltage, and this is going to be the current I. All right, and so I'm going to connect these two to this scope over here. And again, remember that for getting to get multiple signals on the same scope, you can right click on it, go to signals import, number of input ports, and then select 2 or 3 or more, however many you want. Let me make this a little bit bigger. All right, so now I have my scope and my signals being fed to it. Now I forgot one more thing, so let's go back to the library browser, and that is a ground block. So I need an electrical reference, which is this one over here. So let's go back into the model, and last but not least, let's connect the ground reference. Now again, this solver configuration block, you essentially have to connect it to somewhere in the physical network. So in this case, in this circuit, it can be anywhere. It can be here in the ground, it can be up here, it can be connected here to the resistor. It doesn't really matter as long as it touches the physical network. Now, I personally like to always connect it, if I'm doing a circuit like this, just connect it at the beginning where the source is. All right, so I want to talk about this switch for a second. Again, basically what that switch does is it's an open circuit, so that we essentially don't have a complete circuit over here for current to flow until we tell this signal to go above a certain value. And what that value is this threshold over here. So essentially when the input to that port is greater than, in this case, 0.5, the switch becomes a closed circuit. Now we can make this threshold whatever we want, but let's leave it at 0.5. So what I'm going to do then is I'm going to feed the clock, which again is the simulation time, into this port over here. And notice that I cannot connect it because again, this clock is a Simulink signal, but the switch is a physical signal, or rather the port takes a physical signal. So I'm going to add this converter over here, which again is a Simulink to physical signal converter. And now I'm able to connect the clock through that converter to the switch. So again, essentially what this is going to do is this clock is simply going to add, or rather output, the simulation time. So if we're running a simulation from 0 to 1 second, it's going to start at 0, and then as we go through the simulation, it's going to output whatever the simulation time is. So in this switch, I have to find the threshold to be 0.5. What that means then is that once we get to the simulation time of 0.5, then we're going to exceed the threshold of the switch, which again is this 0.5, and the switch is going to close. So essentially the way we've set this up is this circuit is not going to be complete until 0.5 seconds. So for half of the simulation, if we run the simulation for 1 second, for half the simulation, the switch is going to be open initially, and then it's going to be closed after 0.5 seconds. Now I said that I wanted this voltage source to be 10 volts, so let's change this. And again, you can double click on each component. I want this to be 1 ohm, and I want the inductor to be 1 millihenry. So I can either do 1e minus 3, which means 1 times 10 to the minus 3, so 1 millihenry, or I could do 1. And let me just get rid of this. So 1, and then change the units here. Instead of being henries, I can select millihenries. And it's the exact same thing. It's just 2 ways to do the same thing. Same thing here for the capacitor. I can either do 1 e to the minus 3, or I can do 1 and then change the units to millifarads. So just to make it a little bit different than the inductor, let's just leave it at first, and I'm going to do 1 e to the minus 3. Again, it's the exact same thing. All right, so now our model is complete. Again, we have a 1 ohm resistor, 1 millihenry inductor, 1 millifarad capacitor. We have a voltage source. That's a DC voltage source, so a constant voltage source of 10 volts. And we're essentially having a open circuit from t equals 0 to t equals 0.5 seconds, and then we close the switch at 0.5 seconds. And then after that, the circuit is complete. So that's when we should see the current flow. And then again, we're taking measurements of the current and the voltage, and we're feeding that to these two go-to blocks, which are over here on the right in the scope. So let me go ahead and open the scope, and we'll run the simulation from the scope. And again, for scope, since I have two signals, I'm going to change the layout, and I want one on top of each other, or rather one above another one. So the top trace is going to be, in this case, the voltage. Bottom trace is going to be the current. All right, so let's go ahead and run the simulation. It's going to compile and then run the simulation. And let me make this a little bit bigger and move it to the right. So again, top trace is the voltage. Bottom trace is the current. So again, notice that both traces start at 0. And that makes sense because we're measuring the voltage across these three components over here, but the switch is open prior to 0.5 seconds. So the voltage across those components is 0 volts. Then after we close the switch, we're essentially applying this voltage to this entire connection over here. So the output, the voltage across these three components, is simply going to be the same as the input. And you can see that over here. So we have 0 volts from 0 to 0.5 seconds. Then we get a jump to 10 volts, and it stays constant after that. Now the current is a little bit different. So we have 0 amps, of course, prior to the switch closing, because of course, if the circuit is open, or rather if the switch is open, there isn't a complete circuit. So there isn't anywhere for current to flow. So the current is 0. Once we close the switch, then the transient response of the circuit is going to be dependent on that equation that we derived earlier, that differential equation, second order differential equation that is. And the current is going to be given by that equation. And we can see that over here. Again, we were expecting, let me actually go back to the lecture over here. And let me scroll down. We were expecting something like this, 0, and then a damped oscillation that eventually settles at 0 again. So let's see if that matches our simulation. Let me go back here to the scope. And you can kind of see that here, but let me zoom in. So to zoom in on the x-axis, what you can do is you can select this tool over here, which says Zoom X, and then you can click and drag to where on the x-axis, in this case, it being time, where do you want to zoom in. So let me zoom in a little bit more. So this is essentially going from 0.494 seconds to about 0.51 seconds. And we can see that this matches the plot that we had over here on the left, which is, again, what we were expecting based on our circuit, where we derived this second order differential equation, which essentially tells us that the transient response of the current should look something like this. And again, we're confirming that over here in our simulation, as we can see over here for the current. Again, top trace is the voltage, which makes sense. It goes from 0 before we close the switch to 10 volts constant after we close the switch, because we have a constant DC source. And then the current has this transient response that is given by that second order differential equation. All right, so basically what I wanted to show you here is, again, that when you're trying to simulate things using Simulink, first it's helpful to just have some theoretical background of what you would expect to see from the simulation, and then you can see if the simulation matches that. In this case, it did. Basically, the transient response of the current looks just like we were expecting from the second order